afternoon. Welcome again to Samvaad. Today we have the fifth talk of the theme, namely Vistas in Spatio-Temporal Modeling. Today we have two speakers, Professor Uttam Kumar and Dr. Tanuji Chakraborty, both from IIIT Bangalore, who will be speaking about forecasting the future, a hybridization of classical and ML approach. Professor Jaya Sreevalsan Nair is the session chair for today's talk. Professor Jaya is currently an associate professor here at IIIT Bangalore. She leads the graphics visualization computing lab at IIIT, and she's also the core team member of the eHealth Research Center at IIIT. So without further delay, let me hand over the stage to Professor Jaya to introduce the speakers.
Thank you, Nikhil. So it's my great pleasure to introduce the speakers of today's talk in the series called Vistas in Spatio-Temporal Modeling. So we have with us Professor Uttam Kumar and Dr. Tanuji Chakraborty from IIIT Bangalore. Dr. Uttam Kumar is an assistant professor and has also served as Infosys Foundation Career Development Chair Professor from 2018 to 21. He received his master's degree in geoinformation science from the University of Twente and completed his PhD in algorithms for geospatial data analysis from Indian Institute of Science, Bangalore. He worked as a project assistant and a research associate at IISc Bangalore and was a visiting scientist at IIT Bombay during his PhD time. Post his PhD, he also served or worked at NASA Ames Research Center, California, USA, as a NASA postdoctoral fellow, and subsequently served as a visiting scientist at NASA Ames USRA for almost 4 years. Upon return, he joined back IIIT Bangalore. He has published quite widely, around 30 research papers, 16 book chapters, 65 papers in conference proceedings, etc. He has delivered several invited guest lectures. He has won 5 Best Paper Awards, and he has won several awards as well in the area of geospatial sciences. So to name a few, the recent one is the Indian National Geospatial Award in 2021. He has also won the IEI Young Engineers Award in 2016, NASA Group Achievement Award by NASA, etc. And so his research interests are data science, applied machine learning, remote sensing and GIS, image processing, spatial computing, and large-scale geospatial data analysis. Now we also have with us a very young postdoctoral researcher, Dr. Tanuji Chakraborty, who finished his BSc degree in statistics from West Bengal State University and Masters and PhD from Indian Statistical Institute in Kolkata. His research interests include statistical machine learning, time series forecasting, statistical analysis of networks. He is currently working as the emphasis postdoctoral fellow at the Center for Data Sciences in IIIT Bangalore. And he is also visiting assistant professor at Paris Sorbonne University. He has worked as a consultant in various projects with ITC Limited and Bajaj Finserv Corporation. His research publications are again quite immense. He has 20 articles under his belt, all in international referee journals, IEEE transactions, etc. So today's talk is on forecasting the future, a hybridization of classical plus ML approach. It is an interesting talk. It is going to be about its applications of the old and the new forecasting methods in several domains. So it's highly interdisciplinary, and some of the applications of their approach that they have come up with, which is the probabilistic autoregressive neural net, is something that they have been able to use in economics, finance, epidemiology, etc. So without much ado, I would like to invite both the speakers to take over the stage. Thank you so much.
Thank you, Professor Jaya, for the elaborate introduction. And good afternoon, everyone. Welcome to the Samvaad series on Vistas in Spatio-Temporal Modeling. I, along with my colleague Dr. Tanuji, are going to jointly present our work on forecasting the future, a novel hybridization of classical and ML models. So before I start, I acknowledge my colleague Dr. Tanujit for providing the contents of the slides and for the nice slide design. Our talk is spread in two phases. In the first phase, I will give a brief introduction to the history of forecasting. And in the second phase, Dr. Tanujit will present the insights of the classical and ML models used in forecasting. So let's start. There are several buzzwords which we come across every day, especially in the data science stream. And statistics, as we already know, is a study of collection, analysis, interpretation, and organization and presentation of data. As a technology, statistics has wide applications in spatial science in the form of spatial statistics, natural science to human welfare. And data science, as we all know, is the technique of extraction of knowledge from data. And currently, this technique has been extended to the domain of big data. Machine learning, as we already know, and most of us are aware, is actually a set of algorithms that can improve automatically, and we are able to learn and adapt without following explicit instructions. That is through experience and by the use of data. AI is again a study of intelligent agents. So any device that perceives the environment and takes action accordingly to maximize its chance of success. Forecasting is again a term that has been used widely among statisticians. Is how to estimate or estimating how the sequence of observations will continue in the future. So we assume that we have previous sequence of observations and that will continue in the future. So common examples are rise and fall of exchange rates, outcomes of elections, or winners and losers. This is something for everyone. Now let us come across few statements that have been made by popular celebrity around the world, and we see that a, a statement that is related to forecasting often works towards the reputation of a person or against the reputation of a person. For example, the statement made by chairman in IBM in 1943, I think there is a world market for maybe 5 computers. And then subsequently, he had to step down. Chairman of IBM had to step down because of giving a wrong forecasting. President of DEC in 1977 stated that there is no reason anyone would want a computer in their home. And later on, DEC was bankrupted and IBM took over this great company. Steve Ballmer, CEO of Microsoft in April 2007, forecasted that there's no chance that the iPhone is going to get any significant market share, no chance. And then he had to step down and Bill Gates took over as the CEO of Microsoft. And finally, a statement by Donald Trump, where he said that we are going to be opening relatively soon. Virus will go away in April. And in the following year, he had to step down as the president of US, and then the new president took over. So we see that wrong forecasting can actually mar the reputation of a person, and prediction as such is very difficult, especially if it's about the future, as stated by Neil Bohr, who was a Nobel laureate in physics. Now let's look at some of the interesting facts in the past about forecasting. And we all know that forecasting is a term that has fascinated not only people in history, but even fascinates people today. And there is 1,000 years history behind forecasting. Some people consider forecasting as a sign of divine inspiration, and sometimes it is also seen as a criminal activity. The Jewish prophet Isaiah wrote in 700 BC, tell us what the future holds, so we may know that you are gods. And then 100 years later in ancient Babylon, forecasters would foretell the future based on the rotten sheep livers using the distribution of maggots. As you can see in the picture here, this is a clay model of the sheep's liver stored in the British Museum, which shows the pattern of maggots and how was forecasting done at that particular time. Later on in 800 BC, a priestess called Pythia would answer questions about the future at the temple of Apollo. And she was also called the Oracle of Delphi. And she used, some believe that she used hallucinogenic gases that would keep up to natural events. And then she used to do the forecasting. Good examples from ancient Greeks are that people had developed something like predictive models of the cosmos, which is also used in. So they believe that celestial bodies actually move around the Earth, and the Earth is stationary. So this model by Ptolemy became the official model until the Renaissance, when Copernicus, Galileo, and Kepler came up with the alternate theory. Forecasters had tougher time later on, and during 357 AD, an emperor called Constantius uh, uh, decided that whoever does forecasting or whoever seeks forecasting will be silenced forever. There are other stories from England in 1736, when the British Warranty Act in 1736 came into picture, and they said that it's actually a fraud of doing forecasting by charging money, and they had a punishment of 3 months and also imprisonment with hard labor. So as you can see here in this particular cartoon, that lady who is using pistol mumbo jumbo is asking whether the person seeks that or through seeks forecasting through a statistical probability. Funny incident happened in Russia in 2006, when a woman had planned for a outing based on the weather forecast, having a nice sunny day, but soon she realized that the whole day it poured and it got cold. So she actually sued the weather forecaster in the court to pay for the cost of her travel. So there have been several incidents in the history where people had used several ways, several tools to do forecasting. And then there have been several instances where the forecasters or the people seeking forecasting had to be punished in different ways. So the takeaway message is that forecasting is not easy, and then one has to be very careful while doing forecasting. Now let us come across a few terms that are often used while discussing time series models in forecasting. And when we talk about time series data, it is actually a set of observations being recorded at a specific time. Very common examples are unemployment, GDP of a country, exchange rate, and so on. On a similar line, when the time series is discrete in nature and the observations are made at discrete set, it's called a discrete time series data. And all of the examples that I just quoted are of discrete time series. So here the space between the subsequent observations can also be irregular. Continuous time series data, for example, ECG graph is obtained through continuous interval on times. And on a related note, forecast is an estimate of the probability distribution of a variable to be observed in the future. Having seen some of the basic definitions involved in time series data analysis, let's look at the science of forecasting. During close to 1980, during 1980s, people realized that if you actually gather ideas from different fields and then you collect them as a computational and numerical techniques and then analyze them with scientific thinking, then forecasting can be altogether a new scientific discipline. So a time series data may be decomposed into a signal where extrapolation can be done through forecasting. Plus, the second component in the through decomposition is the noise, which is some confidence interval that accounts for the uncertainty in the model. Let's look at one of the graphs showing the total short-term visitors to Australia. On the x-axis, you have month, and y-axis is the number of visitors in thousands. So here we see that a simple exponential smoothing model was used, and the trend shows that in the month of January, that is in winter, there are a large number of visitors going to Australia. But suddenly, during January 2020, the model prediction goes wrong because of the COVID, and it was realized that all mathematical statistical models are actually simplifications of reality, and it is more often than not difficult and complex to model these kind of phenomena. So something is easier to forecast if we have a good understanding of factors that contribute to the phenomena or that can be measured. There is a lot of data available. The future is somewhat similar to the previous, to the past, and the forecast not affect the thing we are trying to forecast. So for example, Warren Buffett makes some comment that stock price may change. So here uh, the forecast can affect the thing that we are trying to forecast. Last one point is, when should we give up? When there is insufficient data or when the models give implausible forecasts. Now let's look at some of the spatio-temporal phenomena and the science of forecasting involved in those models. So a large number of studies currently going around the world involve time series data in spatial domain related to monitoring global drought or climate downscaling or the tropical rainfall measuring mission and so on. Google, for example, has put a lot of research and lot of products based out of research into the public domain for carrying out interesting time series animations. Google Earth Engine has petabytes of data of the order of 5 million satellite images for the last 40 years for the global scale data analysis. As such, they also provide climate and weather data in the form of GridMet or GPM, global precipitation measurement, through the GPM5 version, and they also provide time series wall-to-wall imagery that have been acquired from a variety of space-band satellites. The related studies with these time series data are very interesting. For example, the popular study by Matt Hansen from University of Maryland, who did a global forest cover change across the globe, and then related studies on generating land cover database, a cropland data layers, or even the nighttime datasets being captured from the BMSP OLS data since 1992. They have wide applications, including looking at the ways cities have grown or the ways in which urban sprawl have taken place. Time-lapse is another very interesting application by Google, and there have been numerous case studies across the world to look at different phenomena. Here is an example to show the expansion of Bay Area, the Silicon Valley in US, and the Silicon Valley in India, Bangalore. So here, time series data have been used to develop spatio-temporal models to study the landscape dynamics. As you can see, the overlapped time series data of these particular areas shows across the time how have the landscape changed, and how in particular in Bangalore it is showing how has the Belandur Lake changed across the last 40 years. Other popular studies are looking at the deforestation in Brazilian Amazon, or looking at the heat wave across the globe, the surface temperature, or looking at the climate change across the globe. So these answer different questions, not only looking at the trends, but also they tell us about the situations that have evolved over a period of time or over a period of century. For example, climate change or the global snowmelt. There has been a very popular historical example that defines some kind of a spatio-temporal association between the data, and also looks at the spatial autocorrelation. A popular example that happened in London during 1855 was a classic case which was made by physician John Snow, and this was done when it was realized that people in and around that particular area were suffering from something called cholera and were dying. So physician John Snow very nicely came up with a GIS map where he showed the road networks shown by the lines here, along with the houses and the water pumps. And later he found that there is an autocorrelation between the people's death and the presence of hand pumps, which rather proved to be true than the particles in the air. Other similar examples has been of the Gondwana land, where it is believed that all the continents form one land mass, and over the years they have spread. Similar examples in 1909 was from Colorado, where they found that the presence of fluoride and healthy gums are autocorrelated, because the people staying close to Colorado River, as seen from the time series data, used to consume water that had high content of fluoride, and that led to unusually healthy gums. From all these spatio-temporal models and the time series data, definitely a very nice spatial association is revealed. It also tells us about the co-location pattern. A classic example is trying to map the COVID hotspots in and around the world. Other case studies include spatial classification and spatial trend analysis that are also done through the spatio-temporal models. Now, what can we forecast? Can we forecast the weather? Yes, through the different climate services. Can we forecast the stock exchange prices? Can we forecast the market? Time series models have been extensively used in pharmaceutical industry to look at the forecast in predicting demands for items. Can we forecast the electricity demand? We have seen through some power grid examples that that some kind of a models have been developed, and they have been used, they have been deployed to estimate the power generation, to estimate the power consumption, and hence to plan the power generation capacity and whatnot. We have classic case studies across the globe from time series COVID data for the for predicting the next wave, next COVID wave. So related to similar study, I will now request Dr. Tanuji to present insights of our work done on hybridization of classical and machine learning models for time series forecasting.
Thank you, Uttam, for the nice introduction on time series and the brief history about time series forecasting, as well as spatio-temporal time series as well. So in the second section of the talk, I'll just briefly introduce you with one of the very recent work on probabilistic autoregressive neural network model for time series forecasting, which just got accepted in IEEE IGCNN conference 2022. To begin it with, I'll just give a brief highlight of the things that are there in the paper. So forecasting time series is usually presenting a very recent emerging field which talks about forecasting of the future, ranging from stock price, exchange rate, to the forecasting the regular pandemic cases, the number of hospitalization, and so on. So maybe during pandemic, we have seen a lot of forecasting went wrong, just like Uttam mentioned about the forecast that Trump made, and Trump lost the election. And then after that, so it was all about how accurately you make the predictions, right? So numerous statistical and machine learning models have been proposed in last 5 decades with the demand for generating high quality and reliable forecast. However, in real life situations, when we'll have the situations that both the statistical and machine learning paradigms, they are like either working differently, or they are working for different problems and helping out to solve different problems. But if we can try to make a bridge between them, if we can create an ensemble between the classical approaches and scalable neural network approaches, then we can gain a lot from there. So to fill this gap, we introduced a very very easily understandable, interpretable probabilistic autoregressive neural network model, which is scalable. So it works for different like numbers of data. So if you put say 100 of time series observation, and if you work with 100,000 of observation, for both the cases it works. It's a whiteboard like framework, like we can write the mathematical expressions properly from one input layer to hidden layer to output layer. And we can really handle all the irregular time series component data sets, just like the data sets having nonlinearity and nonstationarity of the data. So what type of data we took for our exercise? We started working with US bath data, which is a very standard data available in R package baths. And this is the data which comprises of number of baths reported daily in the US during 1968 to 1988. Then we started capturing the data called stock price data sets, where we gathered all the data sets from stock price of say Microsoft Corporation, Tesla and Netflix from the Yahoo Finance data, and it has been calculated accumulated from the time period of 2011 to 2021. Then we also worked with Bitcoin price dataset. These datasets are already available in Yahoo Finance, as well as you can get it in Kaggle as well. The datasets comprises of daily close price of Bitcoin. We collected the data from 2013 onwards to 2021. We also like to make our view broader and to work with a large variety of data. So we also captured some of the dataset from epidemiological sector. That is the dataset from malaria, dengue incidence cases of Colombia and Venezuela. And we also gathered the exchange rate datasets. So the exchange rate of ruble versus the USD, the Chinese currency versus USD, like that from Fed database. So all these are publicly available databases. So in case you are interested, anyone is interested to work on time series forecasting, they can just grab those datasets from this particular repositories if they want to work on real life time series forecasting. So what are the common things among all these datasets? So one thing that was common in all these datasets, that all these datasets are non-stationary time series, and all these datasets were non-Gaussian time series. Along with that, we applied one particular non-parametric statistical test, Tera's Vista test, to check the nonlinearity of the time series. And we found out that most of these datasets are actually nonlinear in nature. So the kind of model we are going to develop here, we are going to talk here, is more about forecasting nonlinear and non-stationary and non-Gaussian time series. So if the time series is linear, say some of the classical statistical tool will outperform ours one. If the time series is say a particularly stationary, then suppose some of the other techniques will outperform our method. So we are assuming beforehand that we are going to deal with the datasets which are nonlinear, non-stationary and non-Gaussian dataset. To make the like search space exhaustive, we took all the datasets from several other disciplines just to make and bring the paper rich in the sense of experimental evaluation. And as you can see, the training size of the dataset are varying from say 250 to say more than 5,000. So that's how we took the data, so that we kept on increasing the training and test size, so that to see how scalable our framework would be. So what are the forecasting tools that people have been using so far? So to give you a brief about the tools that are available before 2000 are the following. It starts from exponential smoothing model by Brown, Hall, Winter back in 1956. Then there came the very popular autoregressive integrated moving average model by Boggs Jenkins in 1970s. And if someone wants to work on multivariate time series, then Boggs Jenkins model have been incorporated in the vector autoregressive time series model by Sims and Granger. Due to this work, Granger also got a Nobel Prize in Economics. Is a Nobel laureate. And there are another papers on nonlinear time series models, which are nonlinear ARIMA models proposed by Tong, Granger, Hamilton, Terasvita back in 1980s, and forwarded by Arch model, that is nothing but autoregressive conditional heteroscedasticity model by Angel, Boletsev in 1982, followed by some state space model back in 1989. And after 1990s, people started pushing the neural network and recurrent neural network models for the time series forecasting, and LSTM model becomes one of the popular choice for forecasters after 1997. So in this particular slide, if you look at the first 5 to 6 models, they are all known as stochastic or statistical time series model, and the later portions, they are more or less known as the machine learning or deep learning based time series models. So what are the benefits of working with stochastic models? So it's based on empirical data. the objective measure of uncertainty is very clear to us. It's very much replicable, testable, computable. If you run it many a times, you'll be getting the same results. So no other standard error needs to be calculated, standard deviation needs to be calculated for the accuracy of the model. And it is always able to compute the prediction interval. That's a very very nice benefit of this model. And this is why these models are more stochastic and probabilistic in nature. Whereas for most of these machine learning paradigm, which are from XGBoost to the neural network models, they are very smart algorithms, and it makes very less assumption on the data, but it works with huge data sets. So we need a bulk of data set to train these models. It solves the problem which traditional statistical model can't handle, maybe the large data set problem, the nonlinear time series problem, the non-stationary time series problem. And it doesn't actually do any decomposition. It's some of the models are black box models, which are like, if you give an input of time series, spatial time series, the hidden layers perform all the feature extraction and everything, and does the sequential learning and gives us the output. And it has also very strong emphasis on out of sample predictive performance. The test data performance is usually very good in terms of in comparison with the statistical models, and they put less emphasis on the statistical test rather than the prediction. They more work on the prediction accuracy rather than working on the p-values or checking at the which variables are significant, what are the tests being satisfied and all that. So because here we have a set of IIIT Bangalore people who are attending this workshop. So I thought I'll be just giving you what are the very current state of the arts in the market, and what are the very modern toolkit that are available for forecasters. So most of these are developed by people from Google, Facebook, and LinkedIn and all these people. And these are like kind of benchmark these days. So Prof was introduced by Facebook back in 2018, DART by Unit 8 2018, and then a very recent one, I should say, in 2020, ICLR, International Conference of like Learning Representation by NBITS by Element AI and Yusuo Bengio, so the one of the founding father of deep learning. Then CATS by Meta, a very recent one, and Grey-Eyed by LinkedIn. So these are the kind of the very current state of the art forecasters that have been developed. Is very hard to beat many of them, because these are most of these frameworks from Prof to Grey-Eyed, they are mostly deep learning frameworks, though they take a lot of time to train, in at least in our computers and laptops, even with the GPUs, but still these are the like data hungry algorithm, but they works really well for multivariate and univariate time series forecastings. However, if you look at the problems, the kind of problems that we are dealing with, the birth data, the epidemiological data, the exchange rate data, we have very less observations. So maybe the deep learning model is not a very nice choice being a statistician or time series forecaster. So if we have a limited data set, so I'm calling this 100 to 10,000 observations as a limited data in that sense. So if we have the annual type of data, mostly people prefer working with exponential smoothing model, ARIMA model, autoregressive neural network model, LSTM model, all these models. Whereas if we are given with monthly data, we may sometimes work with STL decomposition, ARIMA model, and ETS and ARN and all these models. And for weekly and hourly data, these are like the heuristic that are developed by the practitioners so far, by understanding the data set and application with the data set, that this works better for limited data sets of weekly, monthly, and annual in nature. Okay. So if we are given with this sort of limited data, mostly people go for these models rather than directly jumping for all these deep learning frameworks actually. So in this slide, I present to all of you most of the state of the art that have been developed so far from the statistical perspective, machine learning, Bayesian, forecast combination, and multivariate forecasting perspective. So this is one of my paper that got published last year, where I put all these papers, but I recently added the PARNN model, that is our proposed one. Before that, we worked with some optimized deep learning model that got published in nonlinear dynamics and ARIMA RNN model got published in Physicae. So, but if you look at the statistical model, it starts with naive model, exponential smoothing, autoregressive moving average model, threshold autoregressive model, wavelet autoregressive model, and so and so. Whereas machine learning community, the very recent frameworks are from autoregressive neural network to deep autoregressive neural network model and Prophet models. So our works lies in the combination of both statistical and machine learning frameworks, which has various recent frameworks, just like the Monash University people, they propose something called feature-based F-forma model, which is nothing but a global forecasting model that they generated and which won the M4 competition, which comes second in the M4 competition. And another hybrid model based on exponential smoothing and recurrent neural network model that actually won the M4 competition last year. M competition is market-based competition on forecasting, in which if you participate, you will get a lot of prizes, just like hackathon and all these competitions, but for forecasting. And it's organized globally by International Institute of Forecasters. So though our model doesn't come in the top 3 or top 10 models in that competition, but we can see that ensemble and hybrid models, they are really doing well on the M4 competition and other competitions as well. Just before introducing our model, because our model is an ensemble or a hybridization of two different paradigm. One is statistical model, another is machine learning model. So the kind of statistical model that we used as a component model in our framework is the autoregressive integrated moving average model, which has its roots back in 1970s by Box and Jenkins, and it's a linear regression model, linear forecasting model, which actually works with the past lagged values as inputs, along with the lagged errors as inputs, and it combines both of them to create an framework in which we write the model as ARIMA PDQ model, where P is the AR component, Q is the MA component, and D is the differentiation term, which helps to modify a non-stationary time series to a stationary one. We make some assumptions because it's a parametric framework, it's a statistical framework, and I think like ARIMA is the most popular model in the time series forecasting literature, which most of you have come across so far. So, so this is the very basic statistical model that we have been using in this framework. Whereas if we go for this, that there are the very basic neural network structure that we all have gone through, must have gone through during any machine learning courses, feed-forward neural network structure, where it's created based on some inputs. We generate a hidden layer by putting an activation functions, and we go beyond the hidden layer to output layer. And most of the time for feed-forward neural network, we prefer to use gradient descent backpropagation algorithm proposed by Hinton and Williams for getting the weights calculated and getting the bias term to be estimated. So this is the very basic autoregressive neural network structure that have been proposed based on the neural network model. So this is the autoregressive neural network model that have been proposed in the literature in 1998, which is the modification of the ANN structure for the time series forecasting. So what is the problem with ANN model? The main major problem was because you are putting an input time series, which is say 1,000 observation. So you have 1,000 features to be put in the input layer, and you are going to generate one output from there. So the neural network structure is going to be too big, but the data set is a univariate time series data, right? So to design the hidden layer, to get the to do the replication with the different number of hidden neurons in the hidden layer, it's a complicated task. So to simplify that task, Faraway and Chatfield back in 1998 in JRSSC, they proposed an autoregressive neural network framework just for doing the artificial neural network model for time series forecasting, the ANN structure for time series forecasting. It's called ARNN structure. So what ARNN does, it takes some previous lagged examples. So how many lagged examples you are going to take, that is chosen by autoregressive model. So you take from autoregressive regressive model, you choose the number of P components as the input feature in the in the neural network structure, and the number of hidden neurons. They have found out an optimum value for the number of hidden neurons for this, which is P plus 1/2 for the non-seasonal data. So right now we have a kind of a fixed structure of the neural network in which you don't need to find out the number of hidden neurons in the first hidden layer, and you just need to use the gradient descent optimization algorithm to get the weights values, and you train a kind of non-linear structure of the AR model based on the neural networks. So that got very much popularity as ARNN model or NNAR model in the literature of time series for based on the feed-forward neural network structure to forecast time series. Now, what motivates us to work with the hybrid structure? The major motivation for the hybrid structure comes from that most of the time ARIMA model works really well, but it works really well for linear time series and non-stationary time series. Linear and stationary and non-stationary. So the problem with the ARIMA model is like the non-linear time series, it cannot really model well, and that is why the ARIMA errors, they do not follow no longer the normal distribution or IIT random shocks assumption. So that is the problem of ARIMA model. So what is the problem in ARIMA model? Actually, if you train it with it for a nonlinear time series data, the ARIMA will generate the forecast, which may not be the best because its error is going to consist of some non-random shocks. So that's the problem of ARIMA model. So we tried to work from their perspective. So ARIMA errors, they have some left out non-linearity and non-Gaussian structure, which ARIMA couldn't really model. So due to that thing, what we are going to do, we are going to create a neural network structure where we are going to use the ARIMA residuals as another input set of components. So this idea we propose here, it's a semi-parametric structure where we fix the number of hidden neurons k equal to p plus 1/2, just like proposed in ARNN structure. But here we work with not only with the p lagged values calculated from the AR model, but q lagged values of the AR ARIMA residuals. So right now the model parameters have total p plus q, total number of input vectors you are going to put, input values you are going to put in the neural network. So this is just the modification we have done in the ARNN framework. And the idea actually came from that whenever we have been working with most of these time series data sets, which are limited data sets, of course, it's very hard to beat ARIMA. Even the current deep neural network structure that I have presented to you, if you just take any 100 to 10,000 observation data, it's very hard to beat ARIMA. But it's not very hard to beat if we use ARIMA errors in the artificial autoregressive neural network structure as the input values. So here we created a YT hat is calculated as a neural network model where in the sigmoidal activation functions, instead of using the previous lagged values of AR model, we also use the previous Q lagged values of the lagged errors of the ARIMA residuals. So if you want to study the algorithm, how the algorithm looks like, so it's an algorithm having 3 parameter values, total P number of P number of AR inputs, Q number of ARIMA errors, and K is the number of hidden nodes we are going to use in the hidden layer. So it's a one hidden layer network structure, which is very similar to ARNN structure, but the probabilistic error calculated from ARIMA model comes as an input in the ARNN structure. That's the difference. And why it will always improve that? Because ARNN model itself work with only the inputs of the lagged inputs of the time series, some P lagged inputs of the time series. Instead of that, if we let the machine learn about what errors ARIMA made, which actually consist of enough non-Gaussian and nonlinear structure of the data, then the model could be always giving us the better forecast rather than using the simple ARIMA or simple ARNN model. So that is why the PRNN structure actually works always better than the ARIMA and ARNN structure for the limited data sets. And we actually final forecast we obtain after putting 500 epochs in the data set and validating the results. So this is kind of the P number of input values and q number of lagged errors of the ARIMA model we put in the neural network structure. And we also build the mathematical foundation of the model. So, most of the neural network models, they lacks the statistical consistency and ergodicity and asymptotic stationarity properties what ARIMA and exponential smoothing models have. But we also worked on that. So we tried to prove the asymptotic stationarity of the proposed PRNN structure. And this is more from the theoretical perspective. We tried to show the geometric ergodicity of the proposed model, and from there we tried to comment on the asymptotic stationarity of the proposal. So what do we mean by this geometric ergodicity? So when we observe a time series, so if we can observe a sequence of observations over time, right? So if we take it as a Markov chain, and if a Markov chain exists such that the stationary distribution actually is nothing but converges to the probabilistic limitation probability. So if we take the Markov chain, and if we consider a Bodal measurable set in RP, so p-dimensional real line, so real space, so and the p be the Lebesgue measure, so we can write down that a particular limiting probability, if it tends to, like the conditional probability, if it tends to the stationary distribution of the process A, then we can say that the process is geometrically ergodic. So this geometrical ergodicity actually helps us to show the asymptotic stationarity or the long range behavior of the time series. Or in very layman sense, if we want to understand whether a time series is going to, over the period of time, if you want to keep on generating the forecast, will the variance be going to infinity or not? That's actually is getting checked by this asymptotic stationarity. If the model have the property of asymptotically stationary, then the model cannot have very large variance over a long period of time. So it will not be keep on increasing just like and tending to infinity. That's the the infinite cases I'm going to talk about. So if the Markov chain is geometrically ergodic, then we always say that its distribution always converges to the stationary distribution, and the corresponding time series model will be said as asymptotically stationary. And based on that assumption, we tried to get the asymptotically stationarity property for our model, but by showing the geometrically ergodicity property of the model. So we broke the time series model that we represented at PRNN model. So it has two components. It has the ARP components. It has the ARIMA error lagged Q components, and we write it as a two different decomposition series. And we try to establish some of the results based on for the geometric ergodicity of the process of PRNN model. And based on that, we get the result for the asymptotic stationarity, which looks very theoretical in that sense, but I'll explain what does it mean in terms of practical interpretation. So these theoretical results of asymptotic stationarity is very much important for predictions over a large interval of time. So for example, if we train the network on available sample data set, and suppose we use the trained network to generate new data, both of them will have the same properties of not. So that is what we mean by asymptotic stationarity in time series context. So if we get if we fit a neural network at a PRNN model for the given data set, and based on the network, if we generate some data, both will have the similar behavior. And it also guarantees that the proposed model cannot have growing variance over time, which is very important from the statistical point of view. So any nonlinear time series or linear time series model in the statistical literature, they are always having this particular property, because if the model variance grows over time, so there is no point in understanding the robustness of the model in that sense. So what do we mean by all these theorems that we have derived? Mostly it implies that the memory of PRNN process vanishes exponentially first, the major finding in the theoretical results presented earlier. So it says that PRNN process is ergodic, asymptotically stationary. That means that if irreducible PRNN model is estimated from an observed time series, the estimated weights are not really far from the true weights. So usually what happens in non-parametric frameworks, the most of the models are not consistent. So because if you get the estimate of the model parameters and based on the true estimate, because you no longer work with the assumptions, you work with the data level approaches where the data generating process is mostly unknown. So in non-parametric framework, the consistency of a model is really a problematic thing. So in our model, if we get some observed values of the parameter estimates from the PRNN model and the true estimates, they will be very close. So that is why whenever you fit a model on the data and based on the model you generate the values of the time series, both will be very similar. So that's the beauty of this particular framework. And this also we have studied these results for right now. We are trying to generalize this result for the general case. Initially, we observed it for P equal to 1 and Q equal to 1 case, but slowly we are right now moving towards understanding it for the general P and Q cases, which is very difficult because for the general cases, the assumptions are going to be like here we make one of the assumptions on the errors of the ARIMA model to be bounded. So there, these assumptions will be always replicating, and replicating all those assumptions is very difficult for the general case. So this particular easily understandable PRNN framework have been evaluated based on several data sets that we have discussed so far. So we have tried with several forecasting evaluation metric, RMSE, MAP, MASE, MAP, all this generally used metric that for forecasting evaluation, mean absolute error, root mean square error, mean absolute percentage error for evaluating the accuracy of this model. And these are the results that we have obtained so far. So mostly we were able to beat ARIMA and NRNN always, and most of the standard model, but some of the cases we couldn't beat Prophet model by Facebook, and we couldn't beat SETAR model, self-excited threshold autoregressive model by Granger, and TBATS model sometimes. So some of the deep learning models sometimes outperforms us, but mostly because of the limited data structure, our model actually outperformed most of this model. So if you are working with like very large data set, maybe our model won't be as good as the Prophet or as good as the neural Prophet or other structures, maybe. But for the limited setup, because we are using only one hidden layer structure, right? And in their model, they have more than 100. So it's very difficult to comprise when you are comparing them for the very big data set scenario. So these are the forecasting curves we generated from our model. Mostly for the training data, it's very easy, but mostly forecasting is very difficult. So if there is all on a sudden, there is a jump, just like Uttam already shown an example of particular Australian tourism data. So all on a sudden COVID came and Australia has no tourist out there. So if these are the cases, all on a sudden, just like Bitcoin price goes very high, it's very difficult to get very strong multi-step ahead forecasting. Our model gets really nice out of sample forecast for at least first few days, like first 7 and 10 days. But most of the deep learning models that have been employed in Python and RStudio on MATLAB, they actually assumes that you generate only one step ahead forecast. So don't confuse yourself with one step ahead and multi-step ahead forecast. This particular model can be used for both multi-step and one step ahead forecast. We have shown the multi-step ahead forecast here, but maybe one step ahead forecast will be very looking very alike as the data set available. Now, what is the merits and what is the demerits of our model? So it's mostly useful when we have nonlinear and non-stationary time series. If the time series is linear, we are not going to beat many, maybe the ARIMA model. And we assume that always the ARIMA errors, they are not going to be IID, random shocks. If it is IID, and then the model itself is very similar to ARN structure. And it's a combined structure which incorporates the positiveness of both the models. So that's why it's better. But our model can degrade this performance when suppose the data set is linear in nature, as well as when we have very large amount of data set for which one hidden layered neural network structure, though it's theoretically feasible, but practically won't be feasible to really get all the structure of the data, time series data incorporated within one hidden layer. So what is the further thoughts on forecasting? So these days, machine learning people and statisticians, they are working together, and most of the combination approaches, hybrid approaches, they are coming in the picture. And mathematicians, they are also not too far from right now. Machine learning community, we are also working on transformer and other set of models, physics informed neural network structures for understanding the spatio-temporal and other global warming problems. So forecasting has become one of the particular scientific discipline for everyone, say from engineering to computer science to statistics. So always it's good to have one forecasting course in our IIIT discipline as well for all the students. And maybe my final say would be like this, but I put it as anonymous because that's couldn't be always true, because a good forecaster is not the smarter than everyone else. He merely has his ignorance being organized. So that's what I believe what we are doing as a forecasting. Instead of doing those definition works or the forecasting based on just judgmental forecasting, we are working, trying to make it a probabilistic approach so that we understand from the data, we learn from the data, and based on the data, we try to make forecast. But forecasts are done like always to be correct, but mostly if some uncertainty arises, something like COVID and other things, it may goes wrong. And if I think there are some of the students who are attending this talk, so for them, this is one of the very latest book in 2021 version, forecasting by Rob and George. Rob and George, they are from Monash. So they wrote a very nice books, practical books on forecasting with all the codes and data available. So that's a good thing to look into. Thanks everyone for listening to me for more than 30 minutes or 40 to say. Thank you so much.
So thank you, Dr. Tanujit and Professor Uttam, for the wonderful talk. A big hand of applause. So we are open for questions now. So if anybody would like to ask questions, you can either write it in chat or you can unmute and ask. Meanwhile, Srinath has posted a question. So I think this is probably a question for Tanuji. Some of the datasets were shown as linear and non-stationary. Does this mean that the data values are asymptotically increasing, assuming they are all non-negative values?
Yeah, so all the data sets that we have taken, they are non-negative. That's the first thing to be noted. And suppose here, maybe this is the particular slide that Professor Srinath has been talking about. So this particular MSFT data is linear as well as non-stationary. So by non-stationary, we mean that the mean and the constant mean and the constant variance assumption doesn't satisfy, but still it's a linear trend. So it's actually either asymptotically increasing or asymptotically decreasing. Okay, so he is absolutely correct for that.
Anybody else like to ask a question? Okay, Dipakar is asking, thanks for the interesting talk. Do you foresee there would be any improvement to increase the number of hidden layers slightly, say 5? I guess you can be a forecaster now, Tanujit. So you foresee the number of hidden layers
yes. So right now we are working on something very interesting called wavelet based autoregressive neural network and wavelet based transformer models. So in which we are actually increasing that. So because to beat these Google AI and the Meta and the LinkedIn structure, if you don't increase the hidden layers, you cannot beat them. So right now we are trying to participate to M5 M6 competition, and hopefully we are trying to increase it. Yes, thank you for the suggestion.
Anybody else? Okay, Sona, you can lower your hand and go ahead and ask a question.
Yeah, thanks for the wonderful talk, Professor and Doctor. So my question is about the model that you have discussed. So here, the lagged error seems to define a prior posterior kind of a concept. So how different is the model that you propose from maybe a Bayesian approach to forecast time series?
Yeah, so in Bayesian time series, so it's a proud information, of course. You are correct, it's a proud information. In Bayesian, what do you do? Mostly for Bayesian neural network, we assume that the some proud distribution of the case. Suppose we put proud for the number of hidden nodes. So number of hidden nodes, we try K to be following Poisson or geometric distribution, say, and then we based on that we get on calculating the posterior distribution, and from there we keep on estimating the beta nodes or the set of weights for the neural network, weights WIs for the neural networks. Here, instead of doing that, we are still in the non-Bayesian framework or frequentist framework. We are no longer in the Bayesian framework, but we are using a prior information from Adima coming. So it's not a Bayesian in the sense that we are not calculating any posterior probabilities. We are not putting any prior on the number of hidden nodes, prior on the weights or anything. Some prior information we are putting in the neural network. So it's too far from that. So it's not a Bayesian network, a Bayesian structure at all. It's mostly, it's fully a semi-parametric and frequentist structure with the prior information taken from Adima. Okay.
Okay, thank you. Understood.
Yeah, thank you.
There's a question from Ram. Can it handle perturbation in the data? So I'm assuming it is probably the neural network that you had proposed.
So we haven't actually looked into it. So right now we are still working on it for the full version of the paper. So so by perturbation, I think you mean the most irregular thing, right? So the moving object thing and all these things, right? So we are still working on the robustness of the model, like the model for the outliers, having the outliers, and if you just change the training testing, just like the adversarial attack, all these things, we haven't still looked into it. This is the very first work that was done, and we are still improving it. We haven't done it yet. Okay.
Thank you. Is it open? Can we try, Tanuj?
Yeah, so we have already given the paper link and the code because it's just got accepted last week. So we are just, because in IGCNN you cannot put the paper before getting it accepted. So we just archived it and we are making the code available very soon. Like by this week it will be available. It's already there in GitHub, but we will share the link with you.
Okay,
maybe Uttam will send you the link.
Okay, thank you so much.
So, sir, just like to know, you mentioned that it will work on limited data set, not on large data set. Can you quantify what is a limited and what is a large? You might experimented.
Yeah. So when we have been trying to work with, say, some of the stock prices of, say, minute-wise data, okay, some per minute, some of the stock prices have been observed, and if whenever we are going beyond, say, 10,000 or 20,000, it works, but it doesn't work as good as, say, Prophet, say the n-bits and all these algorithms. So we cannot that time beat, say, n-bits algorithm. Or suppose if we have a set of features observed along with the time series. So in this talk, I mostly talked about the univariate one. Right now we are working with the multivariate setup. Suppose for weather forecasting, we don't always forecast weather just based on the previous weather. Google also takes care about the whether there was a rainfall, whether what was the humidity, what was the sea level, all this excess, it also exogenous variable, it also considers to make the forecast of the weather. So right now, whenever there are a lot of such excess or the exogenous variable along with the temperature that we are going to forecast, that time our model fails. So that's what I'm telling. Fails means in comparison with the very modern state of the art, n-bits and all these things.
So if you quantify that limited and limited, what is the limited?
Yeah. So whenever we try
that
to
quantified result is I'm expecting.
based on
After that, the
based on
model
the
will not
empirical
work.
study.
After this size, after this stage, the model will not work. So my model is efficient enough until this size. After this, it won't.
Yeah. So what we have found out after up to 10,000 values of the time series, our model really beats most of the architecture. Mostly, if the data is nonlinear and non-stationary. After that, it fails actually. So fails to beat the current state of that. So that's what empirically found out. We have no theoretical justification for that, of course.
Okay.
Maybe that is due to the number of hidden nodes. Yeah.
So you also mentioned that you are taking the average of 500 networks. So 500 networks based on the weightage or based on the hidden layer. What is the factor in that?
Yeah. So for each and every data, we create several ARNN structure in the network, and then we combine them. So it's like the weighted value of the YIs are finally recorded. So it's nothing but, suppose we train a model, say 100 times, we take the average. So we run the model for 500 times and take the average for the paper.
Okay. What is the logic behind fixing that 500, sir? Is it there should be some threshold or
no.
You should have got it at one point.
Yeah, so in neural network structure, just like when we have been working with comparing it with the LSTM framework and other frameworks, so the number of epochs for time series is mostly taken as 500 to 1000. So that is the standard one we have taken. We borrowed from the time series data. And Ramesh Kane, he wrote, is the single hidden layer based on extreme learning machine? So extreme learning machine, I think it was proposed by so one of my friends supervisor, Nan Liu, and his supervisor Huang or something from Nanyang Technical University. So their framework is one hidden layer structure, but the weight optimization they use, it's not anyway gradient descent. They use the SVM type of thing, like a large margin thing in the neural network structure for the extreme learning machine. So here we are not using that. It's not extreme learning machine. It's the feed-forward neural network or autoregressive neural network structure with a change in that. So that's why we call it probabilistic one. It's not an ELM one. But ELM also has one hidden layer, of course.
So I have a question. Maybe I don't know too much about the neural network aspect. So usually LSTM is used quite a bit for time series data, right?
Yes.
So how is your how is your neural network different from LSTM, or how do you make a choice between which one to use when?
Yeah. So LSTM is a recurrent neural network structure. So in our case, it's a feed-forward structure. So the ideology is different, of course. And in we don't have any sequence learning. So they have a sequence learning structure in LSTM. So LSTM is data hungry, of course. Ours is not data hungry. It works for, suppose last 100 days temperature you take, you forecast. For LSTM, it will be just overfitting for 100 samples. The forecast will be very bad. Actually, it will be a straight line just. For our case, it will be giving good forecast. So that's how it's different. So and LSTM takes a lot of time to code for to run for even limited data, but ours one is like a fraction of seconds. So you need not to wait for much. So that's how it's different. So one is deep learning approach, another is initial neural network, artificial neural network approach. So it's a very easy one in that sense. But I'll prefer LSTM whenever we have, suppose we have a sort of large amount of data. Along with that, we have a lot of other input features. Just like for the temperature example, if I have humidity, all the sea level, all the other things, I may prefer for going that, because we are still working on the multivariate framework for our framework, PRNN framework still.
So what kind of models would you choose if you have large number of data points and large number of time steps, right? So how do you make a decision on what models to use? Yeah.
So as everyone will say, no models is good, but few are useful.
Yes, exactly.
So box one is obviously true. It depends a little bit on the some of the global characteristics of the data. So we look at the global characteristics. So the first question as a forecaster I will ask, it's a hourly data or monthly data, it's a weekly data, or it's an annual data. The next question I'll be asking, say, suppose what is the periodicity of the data? Does the data has stationarity? Does the data has trend? So based on that, we choose models. So every model has its drawbacks. That's why, like, even if Facebook came up with profit model in 2018, this year they came up with another new model. So because that's not working anymore with their complex data state. So all the global characteristics that defines actually which model to use. So there is a classification that we made one in one of our survey paper to write out for which type of data, which model to choose. It's a decision tree structure. So if the data is this, and then choose this, like that. So there is no global answer for that. That's why hybrid and ensembles are mostly better. On an average, they're better because that's a combination. Okay.
No, the thing that I was asking is, when you say large data, does that imply the size of the data items or the size of the time instances?
So both the things. I mean the dimension means X. We have some features dimension as well. So other features rather than the Y values, the time series values, along with some other observed features and the length of the time series. Say the length is 100,000. Yeah.
So you had mentioned a lot of your work is based on the non-stationarity test that you do on the data, right? And I saw in your table that you had run a particular test. So is that, so do you, I mean, is that a valid thing to do? I mean, as in valid in the sense, it's like foolproof that, you run the test and you get the what do you say, the property of the data being stationarity, or the process being stationarity or not? Or do you have to chunk the data and check multiple times?
So to check stationarity, like just like right now, I think in American statistician and all this in Nature, one of the Nature journal this year, there is a particular article on p-value is no longer correct. Okay, so that's what like many people found out, because statisticians, they look for the p-value of the test. If it is less than 0.05, we reject and accept it's not like that. So which is sometimes incorrect, but these tests these are mostly the kind of test we are using here. It's unit root test. So unit root test assume, like for stationarity checking, we assume the data is linear, and then we test the non-linear, non-stationarity. And there is another sort of test called KPSS test, which doesn't assume that. So there are various tests we went forward. Like there are multiple tests, and along with that, if you look at the actually the data set itself, you can understand it. It's kind of not like it's very heavy. So if you look at the data, if you see, suppose for a year, the mean and variance was say 5 and variance was 1. And for 2013 data, its mean is 25 and variance is something else. So it's changing the mean and variance. So even from the eye observation also, we can try to find out a little bit about that. So both from the plots, both from the statistical test, augmented Dickey-Fuller test and KPSS test, they help us to get the idea about the stationarity of the data.
Okay. So you just take a set of tests to
exactly
establish its stationarity.
Exactly.
So I have no further questions, and I think everybody's asked you a lot of questions already.
No, it's fine.
Yeah, it's been an excellent talk. Thank you so much, Tanujit and Uttam. A big hand of applause, and we can close the session now. Thank you so much, everybody.
Thank you so much. Thank you, everyone.